Here we are on page 3, and we're going to do from 17 down through 34. These are permutations, also known as arrangements or orderings. Just like what we've been doing in the past, how many different orders can we do this, or how many different orders can we do that? So this is ordering things like books on a shelf. In this case, number 17, how many different four-person presidencies? So this is 1, 2, 3, 4 people. And you'll notice, can you make from a club of 27 members? So you could have 27 people be the president, but once you've picked a president, you only have 26 options for the next one, 25, and then 24. Now notice that this is just like a factorial, except we don't have the rest of them from 23 down. So you can punch this into a calculator like, let's punch that in, 27 times 26 times 25 times 24 and see what we get. So the answer is going to be 421200. 421200. So 421,200 different presidencies. Notice we could also write that as 27 factorial over 23 factorial. And notice what that does. That takes 27 and multiplies all the way down to 1, and then 23 all down to 1. And some people find that a little bit shorter. Say 27 math probability factorial divided by 23. And then math probability factorial. And notice we get the same answer. And this is what this formula does. Is if you say NPR, permutations of n items given 4 slots, or of r items with n choices, this is the formula. And notice you can do that. You can say 27 and then math. When you go over to probability, look what's right above the factorial, this NPR. NPR 4. And notice what we get, the exact same answer. So all three of them are the same, but notice that these are all going to be permutations and look just like that. I'm going to enter it in here, even though you could use the 27 NPR 4 formula. I'm going to enter it in like this because it's going to connect to what we're doing down here a little bit more. All right, let's keep going. Number 18. We've got how many different basketball starting rosters of 5 players. Center, small forward, power forward, shooting guard, passing guard can be made from 12 players. So this is going to be 12 factorial over, and then we want to keep the 5 players, so we've got to remove the last 7 of that 12 factorial. So notice it's not 12 and 5. This would be 12p5. It's not the n and the r that are above each other. It's this, and then you divide off what you don't need. So let's punch that into the calculator, and we get 12 factorial divided by 7 factorial. And we get 95040. 95040. That's right. Okay, number 19. How many different ways can we give one card to each of 7 students out of a 52 card deck? Now notice this is very similar to what we did last time where we showed him the card and then replaced it. But here we're not replacing, we're just giving a card to each of 7 students. So in that case we have 52 factorial over 52 minus 7, which is 45 factorial. All right, let's plug that in, and we get 52 math, go over to the probability, down to the factorial, divided by 45 math, over to the probability, and then down to the factorial, enter. And that's a lot of different ways to do that. And we get 6.7 times 10 to the 11th power. That's pretty big. That's a lot of them. Okay, how many 4-letter words? Now, words is in quotes here, meaning just any 4 letters. So when you take just these 4 slots, 26 times 25 times 24. Now notice what's important here. We're not repeating any letters. If we did repeat the letters, we could have 26 times 26 times 26 times 26, 26 to the 4th. But here we're going to take 26 factorial over 22, that's 26 minus 4 factorial. And yeah, we cut off from 22 down. And it equals, let's use the shortcut this time, 26 math probability NPR 4. So that's going to give us 26 factorial over 22 factorial, and we get 358800. There we go, 358,800. All right, how many different arrangements? And notice in arrangements, that's where we're using this, and in ordering. It's going to be different from our combinations later on, but how many different arrangements of 5 books can we put on a shelf if we have 9 books to choose from? We're going to have 9 factorial over 4 factorial. Again, we don't use the 5, we use 9 minus 5. And what does this equal? 9 factorial over 4 factorial is going to be 15,120. Number 22, how many arrangements can we make of 6 students can we make out of a class of 14? So this is like seating 6 students in desks, and we're counting how many different orderings. So if we switch 2 people, how many different arrangements are there? So we take 14 factorial divided by 14 minus 6 is 8 factorial, which gives us, there we have 14 factorial divided by 8 factorial, and we get, oh, that's big, 216,216,0. That was a big one. Okay, good. Now, notice we're going to do a little bit different thing. We're moving, these are permutations, arrangements, or orderings. Now we're going to do it, but now we're going to make them distinguishable. You're like, wow, what is up with that? Yeah, notice distinguishable arrangements or permutations of the letter cheese. Now we can do this. We have 1, 2, 3, 4, 5, 6 factorial is just the normal way of doing it. 6 factorial. However, you'll notice that when the E switches with that E, or this E switches with that E, or this E switches with that E, they're not distinguishable. You have some identical pieces in here. And so we need to make sure and divide out the number of ways the E's can mess themselves up. So let's go back to the factorial on the previous page and say, okay, how many different ways can the E's mess themselves up? That many ways. So we have 6 factorial because we have 6 letters, but these 3 we can't distinguish among how they mess themselves up. So let's do that one. 6 factorial divided by 3 factorial, and we get 120. Okay, let's do dependence. Let's see if we got the same thing. So dependence has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to start off mixing up 10 different letters. Now let's see how many different ways the D's can mess themselves up. 2 factorial. The E's can mess themselves up 1, 2, 3, 4 factorial different ways because there are 4 of them. And the N's can mess themselves up 2 different ways. Is that right? Yeah, and the C and the P, they're by themselves. So this is all letters can mess themselves up in 10 factorial different ways. So that's how many different permutations if we could tell the difference between these E's. But here, this is how many ways the D's can mess themselves up. The 4 are the E's, and these guys are the N's. So there are how many different ways they can mess themselves up that we can't distinguish, so we have to get rid of them. All right, let's put this together. 10 factorial divided by, and then we have to put these guys all together. 2 factorial times 4 factorial, which is 4, we can actually put factorial on there, and times 2 factorial, that's just 2 times 1. So 2 factorial is just 2. So enter, and we're left with 37,800. Excellent. Okay, 25. Now we're going to do Cincinnati. Oh boy. Okay, let's try it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 factorial over. There are 2 C's, 2 factorial. There is 1, 2, 3 I's, that's 3 factorial. And then there are 2 N's, yeah, and 2 T's. Oh boy. Is that right? Did we get them all? 2 C's, 2 I's, nope, 3 I's, 2 N's, and 2 T's. All right, let's punch that in our calculator and see what we get. It's pretty close to what we had before, so let's pull that guy down, second entry, and then notice that we're over here with a 3 factorial, and then we're going to times by another 2. All right, and we get 75,600. Cool. All righty, number 26. Let's do the letters in Academic. 1, 2, 3, 4, 5, 6, 7 factorial, and then divide off 1, 2, 3 A's, so 3 factorial for the A's, 2 for the C's, and I think that's all. Only one D and only one E. Okay, so 7 factorial over 3 factorial, 2 factorial. 7 factorial divided by parentheses 3 factorial times 2 factorial. Enter 420. There are only 420 different ways you can mess up Academic and make them look different. All right, number 27. This one starts to get kind of interesting because notice that we only have 2 sets of letters that we can distinguish, but just like the others, we have 1, 2, 3, 4, 5, 6 factorial divided by the C's can mess themselves up 2 factorial ways and the B's can mess them up 4 factorial ways. Punch that in the calculator. So we get 6 factorial divided by, in parentheses, 2 factorial times 4 factorial, and that is 15. Interesting. Look how small of a number it is once we start. Every letter is duplicated with some other letter. It really cuts down on how many different options there are. So let's try number 28 now. How many distinguishable arrangements of the letters? Let me see, S's and C's. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 factorial over the S's. There's 1, 2, 3, 4, 5, 6 of them. And that means there are 3 C's. Yeah, and these guys can add up to 9. That just means we've used every letter. Notice here we had 2 letters that didn't repeat. Same thing over here. We had 2, 4, 6, 7, 8, 9. There was 1 letter that wasn't duplicated. So let's see what this guy gets us. 9 factorial divided by 6 factorial times 3 factorial in the parentheses, so it's all in the denominator. Enter, and it gets us a total of 84 different arrangements. Excellent. These down here, they are tougher and should only progress if you really want to do it. These are different permutations, and we're going to read these questions and then we're going to reinterpret them so that we can answer them using the permutation things we've done up here. How many different ways can 15 pieces of identical pieces of candy be put into 7 bags? Now I'm going to rewrite this as a permutation. Now if I write an example of putting 2 pieces into each bag, so piece of candy, piece of candy, piece of candy, piece of candy, 3, 4, 5, 6, and then this last guy gets 3. So you notice, you can kind of see that's one way of doing it. Now if I did it again, I could put, say, 3 pieces of candy in this one, and 3 pieces of candy in that one, and 3 pieces of candy in that one, and then this one has 1, and that one has 1, and that one has 1. This is 9, 10, 11, 12, and then this last guy has 15. That's one way of doing it as well. And notice what we really have. In order to make these 7 breaks, it's almost like you could put right in the middle to divide them something I'm going to call a divider. And this is the secret. If we put this in here, all that did was specify which bag each piece of candy was in. And each way of putting the 15 identical pieces of candy is a distinguishable permutation. So in this case, we now have, there are 1, 2, 3, 4, 5, 6 dividers that make the 7 bags. If you could see that, the 7 slots are made because there are 6 different spacers in there. So if I were to say how many distinguishable permutations of this, it would be 15 C's plus 6 D's, so it's 21 factorial over 15 factorial, 6 factorial. And this becomes the little formula. Let's punch that in the calculator. 21 factorial divided by 15 factorial times 6 factorial. And we get 54,264. And that becomes the answer. And it might be a little bit hard to see that each different way of going into the putting the candy into bags is equivalent to a different word that is 21 letters long. But that's what works. So same way here, this is going to be, because of 5 different classes, we would use 4 different dividers. So 17 plus 4, that gives us 21 different ways, total different letters, 17 students that we would consider interchangeable, and the 4 different dividers. So 21 factorial over 17 factorial times 4 factorial. Let's plug that in. And we get 5985. Number 31. We're going to have 18 identical pieces of garbage into 5 trash cans. Again, this makes 4 dividers. 4 dividers, and 18 plus 4 gives us 22 total letters. The identical pieces of trash, divide those guys out, and the 4 dividers. And this equals 22 factorial divided by 18 factorial times 4 factorial is 7315. Number 32, how many different ways could we put 6 cookies into 5 different lunch boxes? Now here's one I can kind of write out so that if you've had struggled seeing where we got this information from, it's going to be, again, 5 different lunch boxes. That's 4 dividers. 4 dividers, and so that gives us 6 plus 4 is 10 factorial over 6 factorial 4 factorial. And so let's punch out that information, and then let's draw out a few of those options. 10 factorial divided by 6 factorial times 4 factorial enters, that's going to be 210. So again, if we have 6 cookies, that's like having 6 C's. And then if we insert these 4 dividers, and I'm going to do them with lines, you can see what I mean here. 1, 2, 3, 4. And now look at what this is. This is, if we call this a divider and divider and divider and divider, this is 2 cookies are in the first lunchbox, 1 cookie is in the next one, 1 cookie is in the next one, 2 in the next one, and nobody, that 5th lunchbox, didn't get any. Let's do another one and see what it looks like. If I were to do a divider here and a divider here and a divider here and a divider there, we have everybody gets 1 cookie and this last guy gets 2. Let's look at another one. If I were to go and put a divider here and a divider here and a divider there and a divider there, notice what now has happened. This arrangement of the C's and the dividers, the cookies and the dividers, means that we have 1 cookie in the first lunchbox, none in the next one, 1 in the next one, none in the next one, and 4 in the 5th lunchbox. So the dividers have separated these cookies up into 5 different groups. The 4 dividers have. So that's where we get that 5 different lunchboxes is equivalent to 4 different dividers, because there are 5 different sections that it is cut up into. So if that helped to see where we're getting these numbers, good. All right, let's finish up with 33. How many different bags can be made from 36 Dum-Dums if there are 10 different flavors to choose from? Ooh, this is kind of a flip of what's going on. So certainly we're going to use the 36, 46. So we're going to have a 45 factorial. But the question is it going to be 36 and 9 or is it 35 and 10? Let's look at it. If you have a bag that has 36 Dum-Dums, if you label each one of these flavors, grape, vanilla, whatever, really, those are the number of bins, if you think about it, or number of slots, or number of bags, or number of categories that we're putting these into. So if you have 36 Dum-Dums, notice that I'll put D's here. So let's say there are 36 D's going along here. And notice that each different bag can be described by a different setup of where you put the 9 different dividers. Let's put it right here. Let's put a divider here and a divider here and a divider here. That sort of thing will tell you how many grape, how many orange, how many lemon, how many butterscotch, whatever. So this is, we're going to do 9 dividers. So that allows us to do 36 plus 9 is 45 factorial over 36 factorial and 9 factorial. I'll punch that in the calculator. 45 factorial divided by 36 factorial times 9 factorial, enter. And that's how many different bags of Dum-Dums can be made with flavors. Ooh, that's a big one. 886, 163, 135. That's a lot of them. Same thing here. We're going to say 62 Skittles in each bag, 5 different flavors. That means there are 4 different dividers. And so we get 62 plus 4 is 66 factorial over 62 factorial 4 factorial. And let's punch that one in the calculator, which equals 720, 720. And there we go. Good luck with